So let's talk about the condition known as electrostatic equilibrium. So go ahead and read all the parts of this, all the conditions, all the consequences of a conductor being in electrostatic equilibrium, and we're going to go through them one at a time. All right, there's a lot of important information here. First, it's got to be an isolated object, so it can't be exchanging charge or anything, can't be in contact with anything else. It's got to be a conductor, so charges are free to move around inside. And then one of the most important parts is this fact that it's got to be in equilibrium, which means that there's no net motion of charge. Maybe the charges are sort of moving around a little bit around, maybe electrons moving around inside their atoms, but they're not flowing in any one direction. And that's going to be our key motivation to understanding each of these statements about electrostatic equilibrium. So let's take it one at a time. So number one says excess charge resides on the surface. So let's draw maybe like a spherical conductor, a solid ball of metal. We're going to put some extra electrons on the surface like so. And since it is a conductor, the charges are free to move around, and these electrons do not want to be near each other, so they're going to repel each other, and they're going to start to move around on the outside, which means clearly it's not in equilibrium, because that would be a net motion of charge. And like this, they're still clustered over here, maybe they're too close over there, kind of far apart over there, and they're going to move back and forth until they separate out. And if it is a spherical conductor, they're going to have sort of a spherical symmetry to it. They're going to be evenly spread throughout on the outside. And now they've settled in, now the system is in equilibrium. And so it makes sense, of course, that all these charges, these excess charges, would be on the outside, because you have to remember, even though I'm not showing it, there's still billions and billions and billions of protons and electrons inside of here. They all sum to a net charge of 0. These are only the excess charges. And if any of these excess electrons were to go to the interior somewhere inside the metal sphere, well, then they'd be too close to other electrons, and they'd really basically just be pushed back out again. And so the farthest they could possibly get from all those other electrons would be the surface. And so this makes sense, right? That the excess charge resides on the surface. Fantastic. All right, let's go to statement number 2, that electric field equals 0 anywhere inside. So, obviously, if you think about a point charge, or even a test charge right here at the center, it would be equally attracted to all these electrons. If they were negative, it would be equally repelled, but test charge is usually positive. The point is that the net force would be 0, which means the net field equals 0 right there at the center. That makes perfect sense. But that's not what the statement says. The statement says the electric field is 0 anywhere within the conducting material, even at that point indicated by the arrow. So let's imagine, for example, an electron, because it's free to move at that point. Well, clearly, it's closer to some of these other charges than it is the others, right? Which means that it would feel more of a force when these ones it's closer to, and feel like a repulsive force generally that way. But now by sigma F equals ma, if there's a net force on this electron, then it would feel an acceleration that way. What would start to happen? It would start to accelerate, it would start to move. But that violates the condition. The condition in equilibrium is that there's no net motion of charge. And so if any of these charges do feel a force there, they would start to move. That wouldn't be equilibrium. And so if they start to move, they feel a force, that means there has to be a field causing that to happen. But the only way for none of them to move is for there to be no force on them, to be no field, which means the field must be 0 anywhere inside. Do you see how that worked? Right? So we sort of took like the opposite situation and said, well, what if that were to happen? Well, that can't happen because that would violate the condition of equilibrium. So if there are charges moving, there's a field inside. But as long as we're in equilibrium, the charges have stopped moving, there can't be any field inside. That's really what we're saying. Now, maybe a stronger way of looking at it is going to Gauss's law. Remember, for Gauss's law, we define a Gaussian surface. Let's imagine some sort of imaginary sphere inside our sphere. And Gauss's law says that the field on the surface of that sphere is based on whatever charge is enclosed. Now, right now, it looks like there's no charge enclosed. But that's not really true, right? Because there's still billions and billions of protons, electrons inside the sphere, which means there's a lot of them in there. But remember, they balance out to 0 because the net charge, the excess charge, is on the outside. So there's 0 net charge here. And then we can just make that Gaussian surface as large as possible. Right? So make it bigger and bigger. No matter what, we're always enclosing a 0 net charge because there's all of these protons, electrons, but they balance out to 0 because the only excess ones are on the outside, right? And that's what Gauss's law says. The field on the surface of this Gaussian surface is only dependent on however much charge is enclosed. And if the net charge enclosed is 0, there can't be any field inside. We can even expand that Gaussian surface all the way till it's just within the surface of the sphere. And once again, since any excess charge resides on the outside of the outer surface, there's still no net charge inside here. No matter how large you make that Gaussian surface, all the way up to the actual surface of the sphere, there's going to be 0 net charge inside. There's going to be 0 field anywhere we look within the conducting material. Now, this works no matter what. This is not just for a spherical conductor, it's for any shape, and it doesn't have to be a solid spherical conductor. What if it's like a hollow spherical conductor? Well, this is just saying that the electric field has to be zero anywhere within the conducting material. So imagine this is like a shell. We're looking at it in cross-section. This is the inner part of the shell that's hollow. This is the conducting shell itself, which we're seeing here in a circular cross-section, but imagine it to be a spherical shell. Anywhere within the conducting material of this metal shell, the field must be zero. That's what Gauss's law says, because once again, we can just build a Gaussian surface there, and there's going to be no net charge. Now, this doesn't say anything about what if there were a charge inside. If there were an actual charge inside, there could be an electric field in this hollow space. But again, within the conducting material, there's going to be no net charge. There's going to be no electric field. Okay. Now let's go on to statement 3. The direction of electric field just outside the conductor points perpendicular to the surface. So here let's make a different shape conductor, maybe like a flat rectangular conductor. Maybe this is one of our oppositely charged parallel plates. And we'll put some excess electrons on it. And we know that, of course, the electrons are going to reside on the surface. And let's say they're on the top surface here. Same thing would happen on the bottom. But let's just focus on the ones on the top surface. So the statement says the electric field has to point perpendicular. So again, let's take the situation of what if it's not perpendicular. So let's draw some field lines that point this way. And of course, we know field lines always point towards negative charges. So the field created by these negative charges point towards them. Let's say they're on some angle. Maybe you don't want to draw them just yet because we already know this is going to be wrong. We just have to prove why we know it's wrong. So remember, we're talking about the surface of a conductor, and the conductor allows the electrons to move freely. And so if they have a field pointing this way, well, there's going to be some component of the field pointing towards the conductor, but then some component of the field pointing to the left along the conducting surface. And charges that are free to move in a conductor feeling an electric field will feel a force in that direction. Really, in this case, since they're negative charged, they'll feel a force in the opposite direction. So an electric field that somewhat points to the left, well, these electrons would feel a force to the right, and they're going to start to drift to the right. But of course, that violates our condition, right? That means it's not an equilibrium, because the equilibrium says we should have no net motion of charge. So what's the only way the electric field could point so that there's no net motion of charge? Well, that would be perpendicular to the surface, so that there's no horizontal components. These electrons feel no electric field. They feel no electrostatic force. They're not going to move. And hence we prove statement 3. And this is important, right? Anytime we draw electric fields, we always want to make sure the electric field lines touch the surface perpendicular to the surface of the conductor. All right, now we go to statement 4. Charge accumulates at sharp points. So instead of a spherical conductor where obviously, the charge is going to equally distribute all the way around, there's no sharp points there. Let's draw some weirdly shaped conductor, something like this, maybe like a guitar pick. So there's a sharp pointy end and a broad flat end. And we're going to draw 2 pairs of electrons, 2 that are clustered on this end and 2 that are clustered on this end. Now, they're not going to be in equilibrium yet because obviously they're going to exert repulsive forces on each other, right? These electrons don't want to be clustered near each other, so they're going to force each other away. And these electrons don't want to be near each other, and they're going to force each other away, directly away from each other. But now we need to look at the fact that these electrons are constrained to move along the surface. So let's break down each of these forces into components. So here we have a component that's sort of pointing along the surface and a component pointing away from the surface. So all I did was I resolved this force into its components. Let's do the same thing here. It's going to have a force along the surface and a component of the force away from the surface. Let's do the same thing for these forces over here. There's going to be a component along the surface, a component away from the surface, a component along the surface, a component away from the surface. And again, the electrons can only move along the surface, right? So these forces, these components of the forces that are pointing away from the surface can't do anything. They're not going to leave the surface. So all I really want to focus on are these components along the surface. So I made them a little bit bolder. Now compare the size of the component of the force here on the broad flat end to the size of this component near the sharp pointy end. You should definitely be able to see there's a lot more force here along the surface than there is force here along the surface. So what are the consequences? Well, these charges that are near each other on the broad flat surface feel large components of the force away from each other along the surface so they can move relatively far apart. These charges that are on the sharp pointing end feel much less of a force along the surface, so while they will separate, they just won't separate as much. And this brings us to statement 4, that because of this, because they just can't push each other as much along the surface, they will separate but not as much, and so basically the charge accumulates here. It's not like they want to accumulate there, they just can't move away from each other as much. Whereas here on the broad flat surface, they can move away from each other because more of the force is directed along the surface and they'll spread out more. So charge accumulates at sharp points and is farther apart on the broad flat surface. Now in terms of understanding these conditions, you don't have to be able to spit them back out. Like, what is rule number 2? What is rule number 3? Something like that. More, you have to understand them and understand the consequences of them. So when we draw fields We want to know that the field line is always pointing perpendicular. We want to know that the charge accumulates at the sharp points. There'll be a stronger field here and a weaker field here, as opposed to a spherically symmetric one where they're going to be evenly distributed. So you just have to be able to use these conditions as opposed to just being able to memorize them and spit them back out.